Oh, before I do that, I want to show you one thing I didn't mention. You'll see this in the homework, but I just want to make sure that it's clear. Uh, we had this derivation for the potential energy. The U is negative G mm over R. If you have a collection of particles, let's say that I have two particles here. They have a mass m1, m2, and then they're separated by a distance r. We'll call this r12. Then the magnitude of their potential energy is gmm over r. Just leaving off the negative, just looking at the magnitude of it, gmm over r. However, if I have a third particle, like let's say that I have a third particle over here, I'll call this m3. The total energy of this collection of particles is the energy due to these two particles. That would be m1, m3 over the distance between them. The energy for these two particles, m2, m3 over r, plus the energy due to these two particles. We'll see that when we get in. Basically the same thing occurs with electric charges. And you'll see a homework problem where you have to calculate the total potential energy of three particles like that. And so that's how you do it. You take each individual pair, each combination, and if you have three particles, then you'll have three combinations. Let's see, if you have four particles, you have more than that. I probably wouldn't give you four on a test just because, you know, there are a lot of different combinations. You have this combination, and this combination, and then you would also have this combination and this combination. So I think that's all. Yeah, I'm pretty sure that's it. So 5. Am I missing one? Oh, right, the other diagonal. So that's 6. Yeah. All right, there's a homework problem like that, but just want to make sure that that's clear. In this chapter, just sort of a quick recap. We haven't seen a whole lot, but some of it's new. All right, we saw the shell theorem. That is that a shell that's empty on the inside will look like a point mass to an object that's outside of it. We saw the universal law of gravitation. F is g mm over r squared. We saw Gauss's law, which says that the flux is equal to g mass enclosed, 4 pi g mass enclosed. And there's actually a negative here. And we also define this flux, and that flux is equal to our field times the area. We'll talk about this more after chapter 1, because we're going to come back to Gauss's law and treat it a little more rigorously, where we actually consider the dot product of the field and the area vectors. Let's see, we also had the escape velocity, where we just set the total energy equal to 0 and then calculate what k must be in order for u to go to 0, the escape velocity. And we defined this gravitational potential energy, negative g mm over r. I think that's all in this first little sort of pre-chapter, chapter 0 we're calling it. Again, we're going to see all this, most of this again, when we deal with charges, and then we'll come back to Gauss's law as well in chapter 0.5, right after chapter 1. All right? So if you haven't gotten it yet, that's okay. We're going to come back to it. This next chapter, chapter 1, a lot of it in the first part of this chapter you've probably seen before, even in like middle school, just sort of basic stuff about charges. But then we'll see Coulomb's, Coulomb's law, which describes the forces between charges. It looks in form just like Newton's universal law of gravitation, just different constant, different numbers that you use. And we'll define electric field. We've already done the gravitational field, so it's going to be basically the same. And we'll calculate what that electric field is. We'll also do something a little bit different in this chapter where we determine the electric field for regularly shaped objects. Well, I think we'll do like a rod, and a sphere, and a cylinder. Which some of those derivations you might be responsible for. We'll talk about that when we get to it. But the first part of this is pretty straightforward, and I think most of you have probably had it in middle school or high school physical science. But you should have, hopefully you've already wrapped up that chapter 0 homework. If you haven't, then just go ahead and do it, you know, in the next few days, so that you don't get caught behind in chapter 1. All right? That is on the website. It's in your workbook as well, but the solutions are on the website as usual. Have any questions, folks? No? All right. The exam's not far away, because, you know, we just have, I think 4 class meetings or so until the next exam. It's the Wednesday before Mardi Gras, is that right? Or the Friday before Mardi Gras? Friday, right. The Friday before Mardi Gras. Okay, so chapter 1 is on electric forces and fields. We often experience the presence of charges, I don't know, lots of different times, like in your car, right? If you have cloth seats and you slide out of your car and then you go to shut it, what happens? You get shocked, right? So we experience charges in that way when you shock yourself on your car. I remember when I was in high school, I went to a boarding school. It was a math and science school, so what we did for fun at night was we'd stay up and we'd do what? We'd what? No, we'd study, right? We'd stay up and study, and we'd stay up like after the lights out. It was a big deal. We took all these great built all these great structures so that our RAs wouldn't be able to see that our lights were on. Do RAs here, do they enforce lights out? They do not, right? Yeah. That's probably best because y'all are adults. But anyway, I remember one night I was up late and my roommate, Chris Reeks, was asleep because he was a good student and he knew how to get a good night's sleep. But I was up really late at night and I looked over at Chris and he was lying in bed and I was kind of bored. It was like 2 o'clock in the morning. And I stood up and I started shuffling my feet on the carpet like this. You ever done this? And I reached over to his ear, and it was so dry that day, and the charges had built up on my body so much that you could see the arc, the little blue spark as it jumped from my finger to his ear, as those electrons jumped from my finger to his ear, and he sort of twitched, and then he didn't wake up. I kept doing it. It was fun. So anyway, so you can rub your feet on the carpet. And you build up this excess of charge on your body. I do this to my wife sometimes, to cousin. And an interesting thing, we'll talk about this when we see the Van de Graaff generator, but if you build up a lot of charges on your body, and then you go to kiss somebody, no, y'all don't do this because y'all aren't married, but some of you married, right? I don't know, yeah, there's one of you, I guess. Anyway, you go to kiss them, and the charges will build up on your lips because you're sort of poking them out a little bit, and they'll jump across. That's why when you kiss somebody, it shocks them. So that's another way that you can experience charges. Let's see, another thought. Oh, I guess, okay. Dealing with charges works best on dry days. Does anybody know why that is? So like when we went to Colorado over the break, we were getting shocked all the time. Does anybody know why in a dry environment you build up the static electricity a lot more effectively than you do in a moist environment? Yes. Right. Does anybody know why dry air is a better insulator?
Because water attracts negative charges.
Right, because water is what type of molecule? It's a polar molecule. That means it's slightly more negative on one side than on the other side. And so if you're surrounded in a bunch of water and you have extra electrons on you, the positive side of those water molecules will take away those electrons. So dealing with charges works best on dry days because water is a polar molecule. So, like this weekend was particularly dry, right? It was like California weather this weekend. And we were in the grocery store waiting in line. A little girl was there. She took my son's fleece jacket and rubbed it on her head really fast, and then she took it off, and her hair, she had pretty long hair. All right, you can't really do that on a really humid day, but on a day like Saturday, when it was really dry, you can do that because those charges don't leave her body as readily as they would on a very humid day. All right, so when a material has excess positive or negative charges, it is said to be electrically charged. And we have some basic properties of charges, which you probably witnessed before. We have both positive and negative charges. Like charges repel. Opposite charges attract. Charge is conserved. That just means we can move charges around, but we're not going to destroy or create charges. We have a similar thing for the conservation of matter. And then finally, charge is quantized. There is no number 6, I'm sorry. Charge is quantized. That just means that charges come in particular quantities. So the fundamental unit for charge, I'll write that on the next page, but we basically have this particular unit of charge, which is called E. And so my charges come in units of plus or minus 1E, plus or minus 2E, plus or minus 3E, and on and on. They come in these particular quantities, and that's based on the charge of an electron or a proton, which is the fundamental unit of charge. But you can't have half an electron, you can't have half a proton. The charge is quantized. That fundamental unit of charge has a value of, it's 1E, it has a value of 1.6 times 10 to the minus 19 coulombs. And coulombs, that is the SI unit that we'll use for charge. It is one of those basic SI units. So you remember last semester we talked about we had the basic SI units, meters, you don't need to write this down, but just to give you some context, meters, kilograms, and seconds, and now we're adding a fourth unit to that, which is a coulomb. So it's a basic SI unit. It doesn't have any subunits. It's its own unit all. So. This is the charge of an electron. So an electron has a charge of negative 1E, and a proton has a charge of positive 1E. I think that's all stuff that y'all know. You probably even know this number, but this number is on your equation sheet in case you forget. But I expect by the end of this semester you'll just know it. All right, let's try this little quick test. All right, so which of these is not a valid charge? Is it 1.6 times 10 to the minus 19, 5.4 times 10 to the minus 19, negative 3.2 times 10 to the minus 19, or 54 coulombs? All right, I'll stop at say 45. 45. Ask your neighbor if you like. No. All right, it seems like that would be the case, right? 54 coulombs. But look what happens if I take 54 coulombs and I divide it by the fundamental unit of charge, 1.6 times 10 to the minus 19. When I do this, I get 3.375 times 10 to the 20th. Or that would be like 3.375 with 17 zeros behind it. Is that an integer value or a decimal value? That's an integer value. So that means that I have, in this charge of 54 coulombs, I have 3.375 times 10 to the 20th protons, right? The next common answer is C. What is this charge comprised of? How many electrons? There are 2 electrons here, because if I divide this by 1.6 times 10 to the minus 19, I get 2. And because it's negative, it's an electron. What does this charge represent? 1 proton, right? And this one represents like 2.5-ish or whatever. I don't know. It's some decimal of protons. So B then is the right answer. Y'all follow how that works? Based on the quantization of charge. That charge only comes in particular quantities. Okay, let's see. How do objects become charged? Objects can become charged by transferring electrons most of the time. Not protons. Typically, this is the case. Because protons are tightly bound in the nucleus. They just don't move around very easily. It's hard for you to take a proton and move it around. Now, sometimes we'll talk about things. If you watch, like, electricity demos on the internet. Do y'all watch static electricity demos on the internet? No. But if you do, they'll talk about, I have this rod, it's positively charged. The way that you get a positively charged rod is not by dumping protons onto it, but instead you rip the electrons off of it. So when we talk about things that are charged, we're almost always talking about transferring electrons back and forth. Early scientists, by the way, thought that protons were being transferred, not electrons, but early, I guess early 1900s. Okay, so insulators and conductors. I think y'all probably know this, but just sort of to make sure that we're all on the same page. Conductors, in conductors, they're characterized by the fact that electrons move freely. In response to other charges. Or particularly, start thinking about this, not really in response to other charges, but in response to their electric fields. All right. Other charges create these electric fields. These fields that describe the electric force around a charge. We're going to define this and talk about what it means. But other charges move in response to these electric fields within conductors. Examples of conductors? What? Metals, right. So that's the big thing. Metals have this property that allows their electrons to move freely. So we'll just put metals there. By the way, if a thing is a good conductor of electricity, it's almost certainly also a good conductor of heat, for the same reason that heat is transferred in metals. Because those electrons can move around freely, they can transfer the energy, the thermal energy of the heat. So metals are good conductors, both not only of electricity, but also of heat. And insulators are just the opposite. Electrons do not move freely. They're tightly bound. And some examples, I don't know what's an example, but rubber, yeah, what else? Glass, yeah, wood, fiberglass too, right? The electrical, the energy workers, they have those big long fiberglass poles to turn those switches off, on and off on the power poles. All right, insulators and conductors, just know, what those are, how they're characterized, and some examples of each. Okay, so back to charging, how things become charged. If one area of a conductor is charged, then the charge distributes itself across the entire surface, our volume. All right, so let's imagine that we have this conducting sphere. In fact, at first we'll just imagine that this is like a spherical shell. So it's kind of like a metal ball that's hollow in the middle. If we put some electric charges on it, what's going to happen immediately is those charges are going to distribute themselves evenly all around that conductor. Okay? If it's a solid sphere, they would instead distribute themselves all throughout the volume. They would all be distributed evenly all throughout the volume of the sphere. When an insulator, on the other hand, becomes charged, charge on an insulator, if I have these negative charges here, they're just going to stay right where they are. That's sort of true. I mean, we'll see when we'll do the Van de Graaff generator in just a minute, that actually on the surface of an insulator, like materials can be sort of partially conductive to electricity, like we'll see with the human body, that charges can move around on the human body. Obviously, are you getting shocked your wife or your husband or your roommate? Okay, we can have two types of charging, by conduction and by induction. And this will probably seem fairly obvious to you right now, but we'll see some questions in just a little bit, sort of exploring how this works and some results or some consequences of it. So charging by conduction requires contact. Let's imagine that I have a charged conductor and a neutral conductor. This charged conductor has electrons on it. When I bring it up close to the neutral conductor, this is what's going to happen. I'm going to get a distribution of charge that looks like that. Now, remember, our protons aren't really moving around, even though I'm drawing it this way. Really what's happening is the electrons are moving over to this side, and it's leaving an excess of positive charge to the left. Now, when I touch the conductor, the electrons that were here are going to travel onto the sphere, and now I'll get those electrons will move on to the sphere, and I'll still have a setup like that for just a moment. And then when I take it away, they all sort of go back to being distributed, but they're going to be now have an excess of negative charge. That's called charging by conduction. It just means that it requires to touch, that the two objects have to actually touch one another. You can also have charging by induction. Now, we already sort of had charging by induction here when we brought this thing up and we set up this distribution of charge on the sphere. That would sort of be charging by induction, but when you take it further and actually touch the sphere, then it becomes charging by conduction. Let me show you what charging by induction is. You start with just a neutral conductor. So here I have equal numbers of protons and electrons. If I bring a charged object up next to it, so I have negative charges here, I'm going to get a distribution of charge just like before, with positive charges and negative charges. And then, if I ground it, we'll talk about what grounding means in just a bit, but also in chapter 4, I think, when we talk about home circuits. But grounding, in short, just means that I'm connecting whatever device it is to the ground, so that charges can move freely into the earth. The earth is like this huge reservoir of charge. It's sort of like a reservoir of water, a big lake. If you put a few drops of water into the lake, it doesn't really affect the level of the lake. The earth is sort of that way with charges. If I put a few charges into the earth, it doesn't really affect the total amount of charge that's on the earth. So that's called grounding, and we do that with our houses too. So if I ground it, these electrons that were here are going to go down into the ground. And that's going to leave a net positive charge. That's called charging by induction. It didn't actually require contact between the two charged objects. This actually remained charged all along. let's try this quick test, and then we'll do a few concept test questions as well. All right, so in this figure, a ball is made of conducting material, and it's attracted to a positively charged rod. What is the charge of the ball? Is the ball positive? Is it negative? Is it either negative or neutral? Or is it positive or negative? Sorry, I'll take this out of your way. There we go. All right, I'll stop in about 5 seconds. 58, 58. Just guess if you're not sure. Okay, yeah, we're sort of all over the board here. Or B and C. All right, so if it's negatively charged, it's going to attract, right? Because that's positive and that's negative. But what if it were neutrally charged? What would happen? Which is what a lot of you want to see. C is the right answer, by the way.
It would just redistribute.
Right, I would get a distribution of charge. This is important, or the key term here, and maybe if you put B, you didn't read this correctly, but it's a ball made of what type of material? Conductor. So in a conductor, when it's inside an electric field, which we'll talk about later, but when it comes close to other charges, the charges will redistribute themselves. So here, when I come up close to this positive charge, I get a distribution of charge that looks like that. And so then that will allow it to attract to the object that's positively charged. So the answer here is C. It is either negative or neutral. Well, let's try a few clicker questions here. Sort of exploring some of these ideas. And again, these are simple ideas, but you might not have seen them for a while. And that's okay. So two charged balls are repelling each other as they hang from the ceiling. What can you say about their charges? All right, a few more seconds. 50, I'll stop. These are in the back of your workbook, by the way. Okay, awesome. D is the right answer. They either are both positive or both negative. Let's see, what do you get when you cross a zebra with a giraffe? And then you say, I don't know. Zebra, giraffe, sine theta. Get it? Cross product? Zebra and a giraffe? You should tell that one to your calculus professor. She would really like it. Okay? Alright, from this picture, what can you conclude about the charges? And just to be clear, these are two separate things, so they're not affecting one another. What can you conclude about these charges? All right, I'll stop at 50. Okay, C is right. Very good. So I just pick a charge. Like I say, for example, this is positive. If that's positive, this has to be positive. So if the green is positive, that also means the purple is positive, or pink, or whatever. So they all have the same charge. You could start in saying it's negative 2, and you'd come up with the same answer. All right. Metal, oh, this is the same as we had before, so I'm going to skip this. But, by the way, what if instead it wasn't a metal ball, but say a wooden ball? What would be the answer to this? It would have to be negative. It couldn't be neutrally charged, because then a wooden ball is not a conductor, and so you wouldn't get this distribution of charge. But in this case, just like we had before, I get negative charges, positive charges in this conducting ball. It's still neutral, but it has a distribution of charge that allows for it to be attracted. All right, let's try this one. I'll stop at 1 minute. 1 minute. Just 3 more seconds. All right, I think C is right. Let's just see. I'm going to mark it, and we'll come back to it. Yeah, that's right. All right, so here, this is like our charging by induction. I start out with 2 neutrally charged objects. When I bring the positive charge up, I get a negative charge and a positive charge there, because all those electrons rush over towards this positive charge. When I take away the wire in between, I still get a negative and a positive. And then when I take away this charged object, it still remains negative and positive. That's charging by, what is it? Induction, right. That means you don't touch. All right, we'll come back to this. Probably next time we'll do Coulomb's law. Let's see. Let's do a couple more things here, and I want to show you this this Van de Graaff generator. So in insulators, the charges and materials don't move. However, as we said, charges might move along the surface. However, when a charged object is brought near to an insulator, the molecules may become polarized. Like this, let me show you. I go down from here? Oh, wait, sorry. So like, for example, if I have this charged object brought out near to an insulator, I'll get a distribution of charge in the insulator. The charges won't move around, but the actual molecules or atoms will realign themselves so that the negative side is up next to the positively charged object. So you can get this effect in insulators. Oops. You can get this effect in insulators where they polarize themselves. The atoms or the molecules will sort of reorient themselves so that they become charged in that way. One more question. Consider this 2 separate arrangements. What is the charge of Q1? It's very similar to what we had before. Actually, let's see. Yeah, right answer. All right, I'll stop at 50. All right, so let's look first. So Q3, let's say Q3 would be negative. That would mean Q2 is what? Positive. So if Q2 is positive, what must Q1 be? Positive. Well, let's imagine that Q3 instead was positive. What would Q2 be? Negative. So if Q2 is negative, oh, not positive, negative. All right, I'm going to try again. Nobody got the right answer that time, or one person did. Oh, I'm sorry. Never mind. I said that it was negative, didn't I? I didn't read the question. Q3 has a negative charge. Yes, I just gave you the answer, I'm sorry. Right, so the answer is A. Sorry about that, I misread the question. So go ahead and put in A, I'll count it twice. Everybody put in A. I'll stop at 45. 45. A is the right answer. Okay, awesome. Okay. All right, let's see. We're going to deal with Coulomb's law, but first I want to show you this because it sort of takes a lot of what we'll do in the next couple of chapters. You ever seen one of these? It's a Van de Graaff generator. It's sort of like a charge elevator. Think of it as that. And it will take charges and move them from one spot to another. You're welcome to come see if you like. You want to come see inside of it? It's kind of cool, actually. Come on. Yeah, all at once. So, you can look inside of this. It's just a big metal sphere. And there's a belt. See, the belt will move back and forth. And as the belt moves back and forth, so once you see, you can step back. It's just like a rubber belt. You can imagine it like you rubbing your feet on the carpet. And there's a little carpet inside this metal box, a brush, that it rubs up against, and it brings electrons. The little electrons jump onto those little metal wires inside, and then they go onto the sphere. Don't touch it.
So that has to be grounded basically in order to keep working.
Right. So I can ground it by I connect a wire to this. You want to come up and see? Let's see how it looks. I've never had it go down so much. You can't really see it. It's jumping from the belt. Y'all get to see folks? Logan? Y'all come on. Alright. So we can show lots of stuff. Basically, it causes a bunch of charge to go onto the sphere. Let me plug this in over here. We're going to talk about a couple of different things in the next couple of chapters. We'll talk about electric fields, which is a force per unit charge. That's like our gravitational field, which you remember was a force per unit what? Gravitational field. What was it? I said it over. Mass, right? Force per unit mass. That's our measure of G. We'll talk about electric fields, which is just a force per unit charge. We'll also talk about potential. You're probably more familiar with potential. We measured in volts, like in the electrical outlet, 120 volts or whatever. Potential, in a similar way to the fields, is energy per unit charge. So it tells you how much energy charges have. So in a 120 volt outlet, you have 120 joules per coulomb. In a 220 volt outlet, you have more energy. You have 220 joules per coulomb. Right? So for example, if I have this going, it can build up a lot of charge. Thing we turn off, we just hit the big button. All go off. Or both little buttons. Alright, so it's building up a lot of charge. So now these electrons are jumping from the big sphere into the little sphere, and then they go down through the wire. For an electron to jump across about an inch of air requires about 20,000 volts. So this is maybe 5, 6 inches. So this is about 100 to 120,000 volts. That's 100,000 joules per coulomb. That's like it. You can also see charges jumping to the wire. See that? In the next section, we'll talk about coulomb's law, describes the force between charges. You can sort of see the pull of the ball here. That's just what the coulombic force is between charges. Okay, so a couple things we can do here. You can map out the electric field around this. So my electric field around this is, we'll talk about this later. The electric field is going to sort of come out and it's going to flow over the charge, and we can map out that. This is just a cup that's filled with little popcorn peanuts. I put it on top here. They're going to become charged, and objects of charge will follow along the field lines, because that's going to be the direction of the force that they feel. Remember, a field is just a force per unit charge. So if I have a force acting upon this thing that's in the direction of the field, then they're going to follow the field. Now it's further complicated because these have mass too, and so they're also responding to gravity. So they're responding to the gravitational field as well. But you can almost immediately see sort of the shape of the electric field as they come out. Oh, that one got stuck. I don't know if I'm scared. I'll see this one. I'm not scared, so I had to make a wig. Show you a couple of things. Oh, some of y'all can try it out too if you want. Stool. So first of all, when I do this, I have to stand on the stool, because otherwise it will, the charges will just move straight through me. It means I'm going to need your help. Is that okay? Listen, it's very important that you don't touch it. Because once you get a lot of charge on you, and it jumps between us, it doesn't kill you or anything. It hurts real bad. All right. I'm going to make sure there are no charges left on this thing. Let me get my mic. This is just a piece of copper wire. This is the kind you have in the house. That just came out of our house. All right. Why don't you go ahead and turn it on? You can turn it fire then. All right. So I can feel like sort of thinking of the feel. I'm getting this excess charge on me. These electrons are all in my hair, and actually they're trying to reach up to the ceiling, and they'll discharge into those metal bands. Now if I have something like a lightning rod, if I have all this extra charge on me, it's evenly distributed all over my body. But when it comes to a pointy surface, because the surface is pointy, I get an excess of charge. Like where those 2 points come together, you just get extra charge built up on it. And that's sort of the idea behind a lightning rod. So see, this is my lightning rod, and it's really pointy at the end. So these charges are building up on the end of this rod. So notice what happens when I cover it up. And then if I release it, it's allowing these charges to go down. What happened to my hair? It sort of fell down. I lost some of the charge. Okay, very carefully. Don't get too close to me. Just go ahead and turn it off. Alright, so now I can take my hands off. It stays up because I'm still grounded. I'm on this plastic stool, so there's not much way for the charges to leave my body except just go out into the air, into the humidity. But when I step down on the ground, they'll go. Alright? You want to try it? It's kind of cool, actually. You just sort of have to shake yourself to get all the charges off. Who wants to try it? Come on, you don't get... See, come on up. It won't hurt. It might hurt a little bit. It won't hurt that bad. It's not going to kill you. Is that better? Just stand on there, Steve. And you can put both hands on it. It's not charged right now, so you can do it. And during the time, you have to keep both hands on it at all times, because if you take one of your hands away, then you have this one situation where you have excess charge here and less charge here, so the charges will want to jump across to you. But if you can take one hand off if you want to just adjust whatever. Okay? You're pretty good here. You can take one hand off and sort of shake your one hand off. Oh yeah. This was my daughter. Yeah. How's it feel? Nothing at all? You don't feel anything? I sort of feel tingling. Alright, let's go. Alright, you go. Done? Want to clear it off? Alright, so you can take your hands off. It's not going to hurt you. But when you step down, those charges will leave you. There you go. Do you feel anything through your feet? Sometimes if you have a lot of charge on you, you'll sort of feel this tingling in your feet. Anybody else want to try? Or who else wants to try? You never get to do this. How many of you have ever done this? Alright, you want to... Who said who that, Jenny? My hair won't stand. It doesn't matter. We get 820, right? No, 825. 825 we get up?
You feel tingling.
Oh yeah, your hair is thin. That's great.
I feel tingling.
Oh my goodness, yeah. Let's see his hair is stretching out. All those charges are trying to get away. That's pretty cool.
Yeah, I feel a tingling.
Yeah, don't touch anything. You feel?
Yeah, something.
Yeah, cool. All right. I'm gonna try this. I don't know if this will work here, but we'll try it out. No, I might be able to make it work. I'm gonna hold this up next to it, so if it's working right. I don't know if it's gonna work. We'll just try it, and if it works, I'll tell you what it did. There we go. So remember we talked about when we have a conductor, we get this induced charge, so it's trapped in here. Every once in a while it gets close to the withdrawal charge. It goes on and on. In that question we had with another ball, that's what's happening here. You get an induced charge, it traps, and then it discharges. That's just sorry. Can you turn it off? Yeah. All right. All right. And then one other thing I'll show you. I think I'll just switch on early. That's okay. So remember, on a conductor, the charges are all going to be distributed evenly. So on something like this, just like with the lightning rod with a piece of wire and all that, because it's pointy on the end, you have those pieces all coming together, you're going to get an excess of charges on the end. Because you just have all these surfaces coming together and they're evenly distributed across all the surfaces. So when it's a pointy surface, you get a bunch of charges all coming together. Now what that causes is, when you get all those extra charges, is they discharge more readily. They leave the surface more readily. And so what's going to happen here is they're going to spit out charges from the end. It's pretty cool. I'll show you. It's just spitting out charges on the pointy end and causing, it's like a little ion jet, I guess is what I call it. All right. Any questions about this? No? A lot of different ideas. The idea of a field. The field is a force per unit charge. And then also the potential, which we're not going to get to until chapter 3. What is potential? What per unit charge? It's measured in volts, but it's in a more basic idea, it's a watt per unit charge. Field is force per unit charge. Potential is energy per unit charge. All right. Y'all have a great day. I'll see you on Wednesday, okay?